Hi everyone, so in this video we are going to have a look about a new data structure which is called binary search. So before getting into what is a BST or a binary search tree, let us figure out a problem with binary trees, right? So for example, you have this binary tree, right? And you have some data 1, 2, 3, 4, 5, 6, 7. So problem with a binary tree is that if you want to do a search operation, right, then this search is an expensive operation. It is going to take order of n time to search for a particular element. Suppose I want to search 7, right, and if you use a level ordered traversal, right, so then you will have to go to every node, right? So the worst case complexity of searching will become order of n, right? So that is where BST comes into picture, right? So BST is a special kind of binary tree with some properties, right? So let us see what it is, right? So it is a binary tree and elements are ordered, right? So elements are ordered such that for a given node, all the elements which are smaller than the current node go into the left, right? So on the left hand side, let's say this data is D. All the elements will have a value less than equal to D, and on the right hand side all the elements will have a data or a value greater than or equal to D, right? So elements are ordered in this manner, right? And secondly, each subtree should be a BST. This is a BST property. Each subtree or this property should be true at every node. Each subtree is a BST. So let's have a look, right? So suppose you have a node 5 here, you let's say have a node 3 here, you have a node 4, you have a node 2, and you have a node 1. Let's say you have something 8, you have 7, you have 6, you have 7.5, you have, let's say, 9. So you can see in this tree it is a binary tree, plus all the nodes in the left subtree of 5 are smaller than 5, all the nodes in the right subtree of 5 are greater than 5, and the same thing holds true for every node, right? If you see 7, right, all the nodes are in the left are smaller and in the right the nodes are bigger, but they should be less than 8, right? Because BST property also holds for 8, right? So all the nodes in this tree should be less than 8, which is the case, yes, right? So suppose if I put a 9 here or if I put a 10 here, right, then although this subtree is a BST, but at this node we are violating the BST property that all the nodes in the left side of 8 should be less than 8. So this whole tree is not a BST due to this node, so this is what a BST is, right? Now we will talk about how this kind of structure will help us to do efficient searching, right? So suppose you have a 7.5 here, right, and suppose now I'm looking for a node with data 7.5. So I start from the root node, I know it is a BST, so I will go to the left hand side, right? I go here, I want to search for 7.5, and the current node has a data of 8, so I go to the left. I am searching for 7.5 and I'm at 7, so I have to go right. So in the worst case you have to travel the entire branch, right, or entire depth of the tree. So the complexity of the search operation would be order of D. This is the search complexity. Now what is the depth of the tree, right? So the depth of the tree in the best case is of log n, right? And in the worst case it could be order of n if it is a skew tree. Suppose all the elements are like this 1, 2, 3, 4, 5 and so on, right? So if this is a skew tree, then it can also take order of n time, but it is still better than binary tree because we are not doing order n work every time, right? But yeah, in the worst case it is same as the binary tree, right? But we will try to maintain by some logic that tree does not get a skewed, right? So there are trees which are called self-balancing trees. So uh, if the length in one side increases a lot, the tree balances itself to make it a balanced tree, right? So if it is a balanced tree, the search complexity is going to be order of log n, and if it is a skewed tree, it is going to be order of n, right? So what about insertion? Suppose I want to insert a new node, right? So I will just travel. Let's say I want to insert 0. So I will check it is less than 5, I go here. It is less than 3, I go here. It is less than 2, I go here. It is less than 1, I go here. So here I insert a 0, right? So this is how insertion goes. And again, the complexity would be order of depth of the tree, and same goes for the deletion. We will also talk about deletion and little later on, right? So in this video we saw what is a binary search tree, how it is better than a binary tree, and how we can perform insertion and deletion in the PST. In the next video we will talk about these operations in more detail with implementation. Thanks for watching.